Hello everybody, this is Mr. Arago. I know it's been quite a while since we've last met. I know things kind of got out of hand with this whole coronavirus thing, but I'm hoping that all of y'all are staying healthy and you and your loved ones are doing okay. For now, we have a cool introduction to limiting reagents, which is a portion of your Chapter 9 in stoichiometry. Limiting reagents are all about when we run out of one crucial reactant in a chemical reaction, but the reaction can keep going if that reactant is in excess. So think about it like an Alka-Seltzer tablet. Put the tablet in, it bubbles, that's your evidence of a reaction. After a period of time, the Alka-Seltzer tablet is the limiting reagent. So that runs out first before the water does, and you have your reaction go until the Alka-Seltzer tablet dissolves 100%. So that's what we're doing today. I'm going to be following the procedure in the laboratory handout. And yeah, so I'm going to try to detach the camera so I can show you what I'm doing. I pulled out the old apron from freshman chemistry at WU. When you take a freshman chemistry course, they make you buy your own lab apron and your own pair of laboratory goggles. So I understand that many of you might not have this, but I figure I might as well be in character for this experiment. So let's see. Dang, almost dropped the camera there. Okay, so this is what we're doing. The experiment has us doing 8 different trials. I've already done the first 4, so I'm going to show you my process for the last 4 trials. I'm going to be recording all of my data in an Excel sheet. So as you can see, the first 4 runs are already good. The things that I'm measuring, we're starting off with, actually here, let's just go through a trial run of the process, and then that'll make it a little bit easier to explain what we're measuring and why we're measuring it. So first off, you want to find a way to measure the mass of your Alka-Seltzer tablet. So I got one right here. I found that almost all of them are 3 grams. So you just weigh one and say that they're all 3 grams. That's cool. But normally you'd want to weigh, per trial or per run of an experiment, you'd want to individually weigh each thing for each of those runs. But in this case, all these Alka-Seltzer tablets are the same, so we're good to go. All 3 grams. So the way this works is we have a list of trials where we increase the volume of acetic acid or vinegar, and we decrease the volume of water. So on trial 5, which is what we're on right now, we have to add 20 milliliters of vinegar and 15 milliliters of water. In the handout, I provided a handy little baking guide in terms of converting teaspoon measurements to SI unit measurements. So each teaspoon is 5 milliliters roughly. So we need 20 milliliters of acetic acid. So for our first run, instead of beakers, I have these nifty mason jars. Figure this is the best glassware you can get outside of a chemistry lab, so seems like a good idea. Alright, now we're adding 4 teaspoons of our vinegar. Okay, 4 teaspoons of vinegar. And let's see, 3 teaspoons of water. All right, so now that is roughly 20 milliliters of acetic acid and 15 milliliters of water. One thing to take note of is the type of measurement tool that you're using. Great thing about qualitative chemistry and cooking is that you don't always have to be very precise in what you do. I'd say for baking, you'd have to be super, super precise, but for cooking, you can kind of, throw measurements to the wayside and just kind of go with it. So that's kind of what we're going with here. When we're doing qualitative experiments, it's okay to estimate and it's okay to cut corners like this because we're just looking for an effect. And in this case, the liquid here is our excess reactant, so it's okay if we're not exactly on the dot in terms of measuring it because it is in excess, so we don't really care. It will always be there. Our tablet is the limiting reactant. That's what gets used up first. Okay, so we measured our Alka-Seltzer tablet, so now we are going to measure the mass of our beaker with the liquid. Okay, 203 grams. So I already have a column for everything. Let's walk through each of our data columns. First 2 columns are just the descriptions of the runs. Those are just our volumes of liquid. Then we have the mass of the beaker in liquid. So that's what we just measured right now to be still 203 grams. Just 203. Okay, let me see if I can zoom in a little bit. Okay, so now I have mass before the reaction. This cell is just this plus this. So that's the mass I have before the reaction because I have the Alka-Seltzer tablet mass plus the mass of the beaker and the liquid before my reaction takes place. And now we are going to place the Alka-Seltzer tablet in the beaker. And as you can see, which I'd hope you'd expect this, the Alka-Seltzer is dissolving in the liquid water vinegar mixture. Pretty typical evidence of a chemical reaction with the evolution of gas bubbles. Check the laboratory handout for the reaction. We're going to go over in a little bit, but those gas bubbles are CO2, and that's the direct product of the decomposition of our carbonic acid, which we've talked about in class. If you can remember, we talked about the decomposition of carbonic acid quite a lot, where you always get carbon dioxide and water. So that's what we're looking at. All those bubbles are just CO2 gas bubbles escaping. I have this little metal straw. I'm going to use to stir it up so we can get that tablet dissolved nice and good. Try not to stir too much because any sort of liquid that you get on your stirring utensil will take away from the mass that you measure. But it's all qualitative, so it's okay if we have a couple things like that. So now let's give it a little stir, and then let's record a final mass. I've been going off of like when you throw this Alka-Seltzer tablet in and it dissolves, there will be like a final sound if you pay attention to the sound. there'll be like a final bubble sound that's kind of noticeable, and then it'll like ease away. So that's what I'm going to be calling the masses, is after I hear that sound go away. So I'm going to type in my 205, and then I have the difference. So the difference between mass before the reaction and mass after the reaction is just the mass of the CO2. Because everything that we added to this beaker is still in there, except for the CO2 gas that escaped. So that difference in mass can be accounted for the CO2, and we have a measurement now, which we're going to be using to calculate the mass percentage of our sodium bicarbonate, which is the original ingredient that makes all the bubbles. That's the NaHCO3. So we're going to walk through the calculations I did to get these numbers here in a second, but I want to do the other trials first. So I'm going to do the last three, and then it's going to cut, and then we're going to resume, and I'm going to show you my data, and we'll go through calculations, and I'll walk you through the reactions. All right, see you soon. Okay, so we are back. I have finished up the experiment, the last 4 trials. We'll show you the data there in a second, but I want to walk you through the calculations first, and this is how you calculate the mass percentage of your sodium bicarbonate. So that's your NaHCO3. We're going to calculate the mass percentage of the sodium bicarbonate in our Alka-Seltzer using only the information we collected about the CO2 escaping during our reaction. So for this calculation, I'm going to write down our 3 important reactions. So this is just the overall reaction with the active ingredients like acetyl salicylic acid. Many of you may be surprised I was able to say that on my first try. It's just because I practiced a little bit. We actually did a cool lab in high school where we made aspirin, and acetyl salicylic acid is one of the main ingredients of aspirin, and I believe Alka-Seltzer usually has aspirin as an active ingredient, so yeah. So this reaction is the main one involving all of our ingredients. So that's going to be our sodium bicarbonate. And then this is our, looks like C9H7 is the acetyl salicylic acid. And then we have our citric acid. Citric acid being one of the main components of all of our favorite citrus fruits. It's what that tanginess and that acidity that we love from oranges and lemons all comes from that citric acid. Very good for you too. It's also a very good preserver. If you want to preserve things, put some citric acid in it. Okay, so these are our reactants. I'm going to write the arrow. Can you guys see that? So these are our reactants. I don't have enough room, so I'm just going to write the products right below it. So let's see. So these are reactants. And now products. Now this is all in the lab handout, so I'm just going through what each reaction is from the lab handout. So what essentially happens is the sodium in the sodium bicarbonate, which is this right here. So the sodium in our sodium bicarbonate reacts with all of our other ingredients, and you see now that our acetylsalicylic acid now has this Na attached to it, and now it is a compound. So I believe now it would just be sodium acetylsalicylate, something like that. I honestly don't know if that's correct, but it's okay to give things a shot if you're not that sure. Okay, so this is our first reaction. Reaction 1. Okay. Usually I write reactions RXN just because it's quicker. I got to find ways to expedite. So it's our first reaction. Let's see, reaction 2 is the next one down. So this is the decomposition of our carbonic acid. We've had many points to practice this decomposition of carbonic acid. The main example I give when talking about decomposition reactions. Okay, so next reaction, and then finally reaction 3. Can you guys see down there? No, not yet. Let me pull it up a little bit. Okay. Now reaction 3 is the reaction between our vinegar or our acetic acid and the sodium bicarbonate. So what happens is you dissolve the Alka-Seltzer in the water so that you can drink it.